Hi, this is another aircraft indicator. Today we will see this altimeter from Intercontinental Dynamics Corporation. So on the front we have the altitude, which is displayed with this needle with 1000 feet per turn, and also by the digital indicator here. We have also the adjustment of the static pressure in millibars and in inch of mercury here. So we can set the pressure with this knob here. There is a switch, standby and normal. So there is a small push button here. This is for test purposes. On the rear of the instrument we have the static port inlet here and the typical connector. So you can see the reference of this unit. This is the 518-16007-162. So the maximum range is 50,000 feet. The minimum is minus 1,000 feet. There is a seal which has seen better days. The interesting thing is that I have the documentation for this instrument. I think that before doing the teardown of this instrument, it can be interesting to see the block schematic. I think it will help to understand what is inside. From my point of view, it is useless to do a teardown if you don't understand how this thing works. Surprisingly, the schematic of this instrument is identical to the schematics of the Collins air data computer. We had seen several videos before. It was the 590D-2, if I remember correctly, but the schematics are absolutely identical. So I don't know if this instrument was produced according to a license of Collins or something like that. I don't know exactly. First we will see the block schematic of this instrument, and after that we will do the teardown. So this is the block schematic. It is not complicated. It is the servo control loop as usual. So this is the transducer here. So the transducer is composed with an aneroid capsule here, and there is a peak-off sensor, which is a kind of LVDT sensor. This is something which is common on all these kind of transducers. One side of the peak-off sensor is linked to the capsule, and the other one, this E stuff here, is linked to a mechanical shaft. The sensor permits to measure the position of the E bar relative to the I bar. So the goal of the system is to move the E bar here using a motor and reduction gears in order to have 0 volt as the output of the EI peak-off here, and in this case the E bar will be in front of the I bar, just in the middle, and the altitude corresponds to the rotation of this shaft. The shaft is linked to the needle here, so the needle indicates actually the movement of the capsule, and the movement is amplified using the servo control. So the altitude is also connected to a digitizer, which permits to have the GIAM code, which goes to the transponder. So the motor is also connected to the generator, which is the tachometer. The tachometer has two different functions. The first goal of the tachometer is to add a given amount of AC voltage as the input of the amplifier in order to stabilize the servo control loop. This is this link here. And it is also used to provide an indication of the rate output. So it will be possible to test this output using the altitude rate I have described in my previous video. It will be also possible to test the digitizer using the small instrument I have designed several weeks ago. At the input of the amplifier here we have a third signal. So this signal comes from the scale error correction electric cam. So this is actually a potentiometer with the different taps. So this permits to have a linear variation of the angle of the shaft here relative to the air pressure, which is measured by the transducer. And we have also an external static source error correction. So this permits to have a correction of the static pressure according to the Mach number, because actually the static pressure which is present on the input port of the aircraft has also a small dependency to the Mach number. So depending on the speed of the aircraft, there is a correction of the static pressure. On this instrument, we have also different outputs. So one is a coarse synchro. So there is a complete rotation of the synchro for a total of 135,000 feet. And we have also a fine synchro with 5,000 feet per turn. So that's all for the explanations. So let's open this thing to see what is inside and if we can recognize all the parts of this block schematic. I bought this thing on eBay USA actually, but unfortunately the seller sent this thing with a very weak package. So actually there was only this kind of stuff outside this instrument, and without any box or something like that, just this thing. And of course this thing fall, I think, several times on the floor, because from USA to France, I think that this thing was on several hands, maybe 5 or 10%. And if there is something which is sensitive on Earth, and this is this kind of instrument with a lot of gears and sensitive parts and a lot of mechanical stuff inside. So actually, this knob was totally bent, the shaft of this knob. And also, this is more important, when I received this instrument, this pressure inlet was bent like this, approximately. So you can see that there is a deformation of the enclosure here. So I have straightened more or less this power inlet. It was very difficult because this is actually this is the input of the transducer. So this is a very sensitive part. So I hope that there is no major damages on the mechanical stuff. You will see. So let's open this thing to see what is inside. Okay, so as you can see, there is a small damage here. I think that the soldering is okay around this pressure input inlet here, because I think that the shock was terrible. You can see this thing is still bent. Okay, so we can see that this thing is crowded. So we have here the electronic board for the servo control amplifier. We have here the motor and the generator, which is normally attached to this motor. It is the same part actually. This is the digitizer. You can see it is written on this part. So this is the potentiometer with the multi-taps. This corresponds on the block schematic to this thing. So this is the scale error correcting. So this permits to correct the linearity of this stuff. And this is connected to several trimmers. We can see these trimmers here. So this permits to have a correction at the given altitudes here. Each tap should be connected to one particular whipper of one of these potentiometers. And we can see with the orange back here, the coarse and the fine synchro here, with the orange back. So everything is here, and this is a small transformer. The most important thing of this device is the motor, of course, which permits to drive the needle, and also the stuff of the pickoff, which is inside this block. We'll open this in one moment. You have also this solenoid, which permits to activate or not the flag here. Let's open the transducer assembly. I don't know how this thing can be removed. I don't see anything. Maybe it is just mounted like this. Yes, okay. Just need to remove this thing. Okay. Okay, so we can see the capsule here. The capsule expands with altitude, because at this altitude here, at sea level, the air pressure is something like 1 bar. So the pressure provides the compression of the capsule, but with altitude the air pressure decreases, and this provides the expansion of the capsule. So we can see here we have a shaft and the capsule is linked. The expansion of the capsule will provide a rotation of the shaft here. Attached to the shaft and there is this I bar. It is in green color, something like that. Just here, I don't know if you can see, maybe on that side can be better here. So you can see just below the E shape here, you have this small bar which is attached to the capsule. So when there is a movement of the capsule, maybe here it's better, there will be a movement here of this plate here. So the pick-off sensor is here, and the pick-off sensor is attached to this stuff here, and this stuff moves according to the rotation of the shaft which is attached to the motor. So when there is a movement of the capsule, there will be also a movement of this thing in order to recover the zero position of the pick-off sensor. So the pick-off sensor has 3 coils, one excitation coil and 2 measurement coils in series and in phase opposition. So when the I bar is centered, the resulting voltage is close to 0, and this permits to the servo control loop to recover the 0 when the altitude changes. Okay, you can see also that the knob is bent here. But I think that there is no major damage on this thing, so I think this thing can work. The test will be done in the next video. It will be possible to test first the accuracy of this thing using the digitizer, and also we can test the altitude rate output using the previous instrument. You can have a look also on the schematics. It is not complicated, actually it is the same as I said to the schematics of the air data computer from Collins. So there is a servo amplifier which is here. It is built with this op-amp. It is a 741, a classic one. So there is a transistor, this output, which permits to drive the motor. So the motor is here. So there is this capacitor which permits to have the phase shift on the reference winding of the motor. So attached to the motor there is the tachometer here, the generator. As for the motor, there is a reference winding which is supplied with 26 volts AC. Actually, if we follow the winding of the motor, it is this line in the middle here. It is connected in series with the winding of the pick-off sensor. So actually the voltage across the pick-off sensor plus the voltage across the reference winding of the tachometer is 26 volts AC. But anyway, it is proportional to the reference voltage. The tachometer is connected to 2 different things. First thing is this amplifier. So this permits to drive this transformer, and the output of the transformer is fed to the rear connector. This permits to have the altitude rate. During the test, this output will be connected to the altitude rate indicator, which was described in my previous video. And the output of the tachometer is also connected to the input of the amplifier through this resistor. So this permits to have a damping in order to stabilize the servo control loop. So this is the classic method. The input of the amplifier is connected to the tachometer, we just seen. It is also connected to the pick-off sensor, of course, which is here. And you can see that the second input of the pick-off sensor is connected to this potentiometer. This potentiometer is the adjustment of the linearity. It is possible to adjust the voltage at each particular tap of this potentiometer using these trimmers here. These trimmers are supplied with this transformer, and the primary of the transformer is connected to the 26 volt AC, and it is also possible to activate or not the correction, because the middle point of the secondary is available on the rear connector. If you don't connect this line to the ground, this will not have any effect, because this secondary will be left open. And we can see also we have these two synchros, the fine and the coarse synchro for the output measurement, and you can connect this to another indicator or something else. So we have the encoder here, so we'll be able also to test this thing. And there is also this circuit which permits to activate the flag, so it is actually identical to the circuit also of the Collins instrument. So there is this SCR. So there are different conditions. So the first condition is the value of the 26 volt AC voltage. The voltage is sensed between these lines using this adjustment. And there is also a condition regarding the servo control loop. The input voltage of the amplifier is fed to this amplifier here. This is this line. So the voltage at the input here is amplified, and we have this transformer, and the output voltage of this transformer is rectified and placed in series with the gate of this SCR. And if the input voltage of the amplifier is too high, that is to say, if the loop is not closed, because when the loop is closed, and we have always a voltage which should be closed to 0, if there is any problem, this voltage can be above a given limit. And in this case, there will be a negative voltage at this point here, and this will prevent the conduction of the SCR, and in this case, the flag will not be activated. So that's all for the schematics. It is identical to the schematics of the AirData computer from Collins, so you can have a look also. So I will place the link of this AirData computer at the end of this video, so you can see if you want. It is something which is very close to this indicator. So I'll perform the test on next video. Thank you for watching and see you next time. Bye.